Hello, I'm Hong Dan. I will present the 3D geometry and the growth of an basement-involved fault network on the intermediate-terrace northwest shelf of Australia. This presentation includes 5 parts. I first introduce the fault network geometry. For basement faults that were subjected into oblique reactivation, they will initially develop echelon faults in the sedimentary cover, and this with continued extension will develop vertical linkage and the lateral linkage, and then finally result in complex 3D geometry. However, not all the faults are actually parallel with each other, and many faults intersect and then develop into fault networks. So, for example, the sedimentary basins that provided by Nixon and Staffy, and even in the unknown modeling, we can see the faults that have different orientations. Here is an example from the Kaiserland, the United States, also showing the faults of different orientations, also fractures as well. On a larger scale, here is the fault map from the Red Sea and the Gulf of Suez, where we can see that the western margin of the Red Sea have a complex nest of fault networks on the margins. Although, whereas most analysis of fault network have been largely two-dimensional, few have shown the development of three-dimensional fault topologies due to limited access to high-quality 3D seismic data. And here we're going to show an example of high-quality seismic data for 3D fault topologies. And also the relationship between geometry of basement structures and overlying fault networks in the sedimentary cover has been later explored. For the fault architecture, we defined the 3 basic geometrical components: the main fault, the splay fault, and the branch line. Main faults look like the strain and most of the displacement. Splay faults are subordinates of the main fault, to which they are geometrically and kinematically linked. The branch line is the intersection between the main faults and the branch lines. We also defined 4 types of splay faults: rejoin splay, divergent splay, and connecting splay. There are 3 types of, we also defined 3 types of branch lines, and the circular branch line, the vertical branch line, and the horizontal branch line. Now I will introduce a geological background of the Northwest Shelf of Australia. Northwest Shelf of Australia is a passive margin in the northwest part of the Indo-Australia plate. Our focused study area is Northern Kanava Basin. The Northwest Shelf and Northern Kanava Basin has experienced 2 main stages of extensions and that are associated with continental breakup. The first one is in the later Carboniferous, started from later Carboniferous to late Permian. This involved the separation of the Silurian from the Northwest Australia. A second phase of extension started from late Triassic and ended in the late Jurassic. This involves the separation of Agaland and the Great India from the Northwest Australia. So our studied area, the Northern Kanava Basin, actually consists of a series of subbasins, and our studied area is the Dampier subbasin. Here I will show in a cross section through the Dampier subbasin to see the base architecture. In the eastern part of the basin is the Mermaid and Intermediate terrace. It's dominated by basement-involved structures, and we can see the Permo-Carboniferous growth strata. The basement structure is also truncated upwards into the Triassic and the Jurassic sedimentary successions. In the Lewis Trough, we can see the later Triassic to later Jurassic and thicker package of sedimentary section. This is the second phase of extinction, syncmatic strata. To the west is the Rankin platform and Exmouth plateau. This place has not been deformed very much, but has a thick package of Triassic successions. Our studied area is the eastern part of the research area of the cross section on the Indo terrace. We use three representative wells to showing the lithologies of this area, and we divide the stratigraphy into four types. And the first one is in the crystalline basement, and at the base, at the deep level, it has a very competent mechanical property and dominated by brittle deformation. On top of that, the wide distributed local share has a heterogeneous mechanical property and dominated by ductile deformation. This is overlined by the Mangalore sandstone. It has a competent property and dominated by brittle deformation. Overlying on the Mangalore sandstone is a sandstone that interbedded with shells, so it has a heterogeneous property and dominated by brittle ductile deformation. The mechanical property this during from late Paleozoic to only Cretaceous extinction direction also changes temporally. Therefore, the change of extinction direction and mechanical stratigraphy actually has an impact on the fault development, and it will be addressed in the following part of the presentation. So our studied area is on the Indo terrace. We use this high resolution 3D seismic data to map the base Triassic. We can see F1 and F4 basement involved faults that are relatively continuous at the base Triassic level. However, these four faults actually become not less continuous, and they become segmented at the mid Triassic level. So from the cross section, we can see that the Indo terrace is dominated by tilted fault blocks bounded by basement involved planar faults that branch upward into the cover strata. In particular, at the lower Triassic to mid Triassic level, the fault geometry concave upward into a complex fault geometry. So our focused area is in the middle of the section. We zoom in, we can see that the top basement level has been truncated, and this involved in the basement fabrics that are parallel with each other, and then this fault propagate upwards and then bifurcate into fault splays, and the fault geometry change at the lower Triassic level. So we then map the key horizons and show the EGU 3D perspective of the faulted horizons from lower Triassic upward to the mid Jurassic. We can see that at the lower Jurassic level, they have a slow-going faults, F1 to F4, that are intersected as a fault network. And in the mid Jurassic to lower Jurassic, and F1 to F4 are actually very segmented, and stepping into the footwall for the splay faults. Also in the mid Jurassic, they have a very clear fault segmentations. Although this displacement of the splays becomes smaller compared to the lower Jurassic and mid Jurassic levels. Using a 3D geobody, we can see that the cross section of the faults and the map view of the faults as well, and it shows the planar normal faults that bifurcate upward in the sedimentary successions, and this develop upward into a complex fault zone that we just shown there in the previous slide. The next one and parts we will showing you the 3D fault network geometry and the growth of fault network. From the studied area, we can see clearly that there are many branch lines. The vertical branch lines have a subvertical geometry and develops when adjacent fault segments are laterally connected through wall bridge of relay ramps. For example, the example A. Horizontal branch line have a subhorizontal geometry and connect shallow and deep fault segments during the bridging of a vertical linkage. And this is particularly true as the basement faults actually have a large displacement, and the shallow faults has a smaller displacement, but were linked in middle in the lower to mid Triassic level. So in this case, they form the horizontal branch line. This example B and example C as well. A trailing segment is a part of the older fault that connect two younger faults. For example, the F1 actually connects F2 and F3, and both at the basement level and the sedimentary level as well. So we interpret the fault horizons, and we interpret the fault surface as well to show them in 3D. We can see that F1A has a planar fault in that basement, and then they were linked with a series of left stepping in echelon faults at the sedimentary cover. And F3 and F4 also have the similar geometry. Have a continuous fault at the basement level, and then we're linked with the right stepping fault segmentation at the sedimentary successions. So yeah, we map all these faults in 3D, and then we plot the displacement. We can see that the displacement maxima is located within below in the Triassic, indicating that these faults were initially developed before Triassic, but they were vertically linked with complex fault segmentation in the upper successions. The fault geometry of this F1 is that they have a typically lower angle at the T10 to T17. This is correlated with local shear, the mechanically weaker layer. Therefore, the mechanical stratigraphy has a control on the fault geometry as well. So for the F2 to F3 and F4, we calculated displacement. It shows similar observation, has a maximum displacement at the Triassic level, and then upwards is dominated by fault segmentations, but the displacement are relatively lower. And also for the strike projection of the fault deep attribute, we show that the fault geometry change at the TR10 to TR17 again indicates that the mechanical stratigraphy has an impact on the fault geometry in 3D. In the middle of F1, we show in the high resolution relay ramp A and relay ramp B. Relay ramp B have been breached, but relay ramp A has not. We're showing that the faults, the relay ramps rotated, and also the faults involved within this fault zone. Again, it shows the displacement maxima at the depth and the lower displacement at the shallow levels, but also the fault train changes as well, and because of the fault array development. Now we analyze the expansion indexes to showing the episodes of fault growth at this particular area. We actually showing that the F1 and its subordinate splays has 3 stages of fault activation. The first one is lower Middle Triassic. The second one is lower Jurassic, and the third one is lower Cretaceous. Therefore, this fault has been reactivated for 3 times, and now we use the thickness mapper to showing the high water center and give the indications for the fault activation. We see that at the lowest Triassic to mid Jurassic levels, high water center are more or less parallel to the orientation of the main faults at the basement level. But at the mid Jurassic to early Cretaceous level, high multiple centers are more or less parallel to the orientation of the fault splays, indicating that the splay fault developed in the early Cretaceous extension. Therefore, F1F, F1G, and F1H, and in the central part of the F1 actually developed later at the later stage of the fault development, indicating that the extension change that developed this fault place. Now we started the entire fault network and to showing the thickness map and the growth of the fault network. We're showing that at the late Upper Carboniferous to Upper Permian, there only the sedimentation in the high wall of F1. Therefore, F1 was only active in the late Carboniferous. However, from only Triassic to mid Triassic, from lower to mid Triassic, we see that F1 will reactivated at the same time. F2, F3, F4 also have developed, therefore developing a fault network at the only to mid Triassic stage. And then from mid Triassic to early Jurassic, the fault was not much active, but the high wall deformation was clear, so it was dominated by high wall deformation, and not not much fault displacement. Now, the fault displacement resumed in the lower to mid Jurassic. We can see that the southern part of F1 and the F3, F4, and F2 were dominated by rapid stepping fault segmentation. In the mid Jurassic to low Cretaceous, we see that F1C, F3D, and F4C were linked as a continuous composite fault, but the rest part of F1, F1F, F1G, and F1H, F1J will characteristically have shown the left stepping fault segmentation. So based on the fault geometry and the fault growth analysis, we conclude that the evolution of F1 to F4 fault network development. Initially, at the late Carboniferous to late Permian extension, they firstly form 3 isolated fault segments of F1, and this will gradually linked. In the only to mid Triassic extension, F2, F3, and F4 were developed, and this were linked with the reactivation of F1, and this formed the fault network at this place. In only to late mid Jurassic extension, the reactivation of the faults developing the right stepping fault segmentation along the southern part of F1, F2, F3, and F4. Although F1, the central and northern part of F1 was also reactivated, but they did not have much segmentation development. In the only Cretaceous extension, the reactivation and developed the continuous segment of F1C, F3, and F4 as a composite fault. But in the footwall, the F1G, F1F, F1H, F1J were left as left stepping fault segmentation. So yeah, we then compare and the other examples, and then we conclude how the faults in 3D were characterized in our fault network development. So here we use the example from WISJAC 2002, the annual modeling showing that the basement faults actually propagate upward, and it shows very complex high wall geometry in the sedimentary section. In the map view, the faults are in echelon, because the extension direction is oblique to the basement, is oblique to the basement orientation. But with continued extension, the basement fault will finally propagate upwards and forming a continuous fault, leaving the oblique splaying faults be activated in the footwall. So this is actually comparable to what we're showing in our study. All these splay faults will gradually have a diminished displacement, and the major fault becomes dominant. Another example is from Giba. He studied the fault reactivation in the sedimentary basin in New Zealand. It shows that the oblique reactivation of the basement fault developed in echelon fault arrays that rotated and twisted towards in a direction that have a high angle against the original direction. But at depth, these faults will connect with the basement fault, therefore developing a twisted geometry in 3D. So in our case, we see that a 3D fault evolution of the fault network follow initial construct of the basement fault network, basement involved faults. For example, the F1, F3, F2, F4. These faults actually construct the fundamental architecture of the fault networks that even the reactivation did not change much because the splay faults developed in the sedimentary successions were gradually abandoned with continued extension. Another very important observation is that the curved fault geometry within the lower to mid Triassic section, because of the mechanical property change, becomes abandoned, and this was replaced by a planar fault developing in the Haimar. In this way, it facilitates the fault displacement transfer between deep and the upper segments, and this finally results in a relatively planar fault in the sedimentary successions as well. So the wrap-up message for this presentation is F1 to F4 is a basement involved fault network that was reactivated in the only to mid-Jurassic and the only Cretaceous stations. Mechanically weak stratigraphy has a strong influence on the fault geometry in the sedimentary cover and develop a concave upward fault geometry. Main faults, secondary faults, and the branch lines are fundamental geometric elements of fault systems that construct the complex three-dimensional topology of fault network architectures. With continued fault growth, the fault network tends to abandon this place and fault surface irregularity and becomes more focused on the development of planar and continuous fault architecture that is favorable for this displacement transfer along strength of steps of the main fault. This is a presentation. Thank you.